Unit 7. So this is something completely different. We're starting on discrete event simulation. Oh, wait a minute. I'm not sure that, just let me check. Oh no, it's recording. Okay. It's like, is everything recording? Okay, it's recording. Great. So let's get started. Yeah, so I guess like what we're going to cover in this unit is we're going to talk about generating random numbers, because that's like kind of a very important part of Monte Carlo simulations, which are all about using random numbers to simulate something. Yeah, so well, why the weird name, I guess. It's the first thing here we're talking about the notes. So Monte Carlo is actually a city. Here it is actually. There it is, down there in Monaco. Oh, I've lost it now. Somewhere in there. So it's an old city, and it happens to have some famous casinos. And so there's like that notion of randomness and gambling. And during their Manhattan project, they were developing the atomic bomb. Some of the physicists wanted to do simulations. And so John von Neumann, and Nicholas Metropolis and Stan Ulam were doing devising new algorithms to simulate some of the things they were doing. And on one of the first electronic computers. And yeah, they chose the name based on the place where Ulam's uncle was wasting lots of money. So yeah, that's why Monte Carlo as a name, and it's also a place. It's a strange one, but basically, when we talk about Monte Carlo methods, we're just talking about using random numbers to simulate things, basically. Yeah. So like one particular type of simulation that we're going to be looking at in this unit is discrete event simulation. And like that often involves random numbers. It doesn't even have to necessarily, but the basic idea of a discrete event simulation is that there are events that happen discretely in time. So there's like sort of nothing happening in time for a while, and then there's some event that happens and that changes the state of the system. And you can know when the next event, generally you can know when the next event's going to happen. So you just advance time in these discrete steps and deal with the events as they actually happen. Yeah, and like why are we looking at this? It's kind of a nice example in terms of structured programming, like using structured programming to solve problems. You can set up some like a really general kind of framework for solving discrete event simulations, and plug in like your particular like problem into that framework. So we're going to see some code later in the unit, like that'll be probably next week or the week. I think it'll be next week. Yeah, we're gonna see some code where it's like general. This week we'll just see some very specific examples. Yeah, okay. So before we go into discrete event simulation, though, we're going to talk about random number generation. And especially like we'll talk about generating uniformly distributed random numbers, and we'll talk about generating them with various different distributions. So I'll show you some tricks that people use to generate random numbers with different distributions. And later on there'll be, so then we'll go like kind of into, yeah, hello, welcome. It's lovely to see people here. I was worried there was only going to be 3 people, so it's great that more people are turning up. Yeah, so later on we'll probably go into Markov chain Monte Carlo, which is like a very powerful way of simulating certain types of systems. But yeah, before we do that, we'll look at like some discrete event simulation code, and we'll try and get through like the core like key pieces of that this week, so that you can start on project 2, because that's going to all be about discrete event simulation. And there'll also be a little bit of computer sciencey / like kind of software engineering-y stuff in there. We will look at the heap data structure, which is one of the ways of making a priority queue, which is a way of making these simulations efficient. Okay, and there's a couple of other like sort of software engineering things, like how to arrange your code into modules, and how to sort of optimize your code and benchmark it. Probably have a look at those kinds of things. And again, we'll be looking at like structured programming, so how to design your types and functions to make sort of generic code. Yeah, okay. Right, so onto random numbers. So there'll be like most of this lecture probably we'll just be talking about random numbers and how to generate them. We generally generate them in a computer using a deterministic algorithm. That's what pseudo-random numbers are. They're numbers that look random, but there's a deterministic algorithm behind there. There are actually true random number generators based on physical devices that you can buy. Like there's those on the market. If you really need an actual random number, probably for like cryptographic purposes or something, then you could buy a little device to put in your computer. But yeah, we won't worry about that. We want to do fast simulations, and that's not what you would use for fast simulations. So we're going to talk about pseudo-random numbers. Okay, so we've got a bunch of code on here, which is irrelevant at the moment. But let's see, is that big enough? Probably. So, okay, let's just go using random. Actually, we don't even need that to call rand. So rand is the function in Julia which generates a random number between 0 and 1, uniformly distributed. So we'll look at a bit about like get a kind of flavor of how you might implement rand, I guess. So this is kind of like the simplest thing you might want, a number between 0 and 1, maybe, or a random integer, maybe arguably simpler, but yeah, so we could like ask a bunch of questions about that, like what, like how does it random, like what is its distribution, and what does it mean to be random? Yeah. So okay, so like when you're looking at when you're generating pseudo-random numbers with a computer, you're really running something along these lines, an algorithm which, so you've got a function which takes a state, Sn, maps it to a new state, Sn plus 1, and returns a random number. So that behind the scenes, when you call rand, is actually a random number generator state somewhere hidden behind the scenes, and it's updated every time you call rand. And what's actually happening is this. So this hidden state is getting updated, and this random number is the only thing that you actually see, and it gets returned. And yeah, if you use a particular version of that state, then you always get the exact same random number for the next random number in the sequence. Yeah, and so like the state itself could be small or it could be large. So if we look at some of the states that actually occur in like the random library. So let's look at random dot XOR XOR. This is the default random number generator, random dot X. I don't know how to pronounce that actually. XOR, who knows? So that's actually a pretty small state. This is like 40 bytes, which is actually pretty small. The previous kind of gold standard that everyone seemed to use was a random number generator called the Mercian twister. And so you might have heard of that one. This is like a bit of internal stuff just to see the size of that state. That's 3,000 bytes of state, which is absurdly large. Now that given that, like, as far as people can tell, this other random number generator is like pretty good properties and has much smaller state. That's really good for various reasons. Yeah, the way Julia deals with these things with respect to tasks and stuff wouldn't really work if we had a huge state involved. So yeah, it's actually really good that we can get one of the more modern generators. Okay. Okay, so what do we actually want this function, which is going to map our state to a new state, to actually do? one of the things you want is that the two different random numbers in the sequence should appear to be statistically independent from each other. So if you would calculate correlations between those, you just don't see any correlations. And for like, because we're trying to build other things on top of this, we want this to be a uniform distribution. So there shouldn't be any values of x which we get out of this sequence, which are like more common than other ones. And we want the range to be well defined. Normally people would like to have numbers between 0 and 1 because that's convenient to use to generate other random number generators and things. The sequence should repeat itself as rarely as possible. Now with the smallest state, you're guaranteed to, well, I guess like we could ask, does the sequence have to repeat itself? What do people think about that? Any thoughts? Yeah.
Like things you say that necessarily like you're going to end up repeating the state at some point.
Yes. Yeah, perfect. Excellent answer. So yeah, just for the people online, the answer is that yes, like you do have to repeat the state because we you have to repeat the values because we only have a finite size in the state. So like for this one, for instance, with 40 bytes of state, you guaranteed to repeat, what is it? You're going to have, so you've got like 2 to the 40, this many possible, whatever. Okay, that's hilarious. Does anyone know what happened? Why that happened? There's just, yeah. Sorry. Yes, it's overflow. Thank you. So we actually need this to be a big num because it's too big. So sorry, that's like a super funny little thing. This happened to be the right number of, so that we would get 0 out. But anyway, so we've overflowed, like flowed a 64-bit integer and we've overflowed to 0. Anyway, so this is the actual answer. So this is like, if you were working with the Exoshiro one, then this is the like possible, this probably isn't, but this is like the maximum possible sequence length that you would have. Which is really big. And I mean, this one here is going to be actually absolutely absurd. Like in practice, those sequences, like the length of those sequences is probably less. I don't actually know what it is. But yeah, if you only have, we'll see a random number generated in a minute where the sequence, like the state is actually the number itself. So then you have only, like, if you've got 64-bit ints, you've only got 2 to the 64 possible values. But still, that's pretty big. Like if you're using a computer to count things and it counts like at a rate of gigahertz, which is 10 to the 9, then like 2 to the 64 is still a big number. So yeah. Okay. Oh, there's one other thing here. So that's like a lot to explain that point, but there's one other thing here, like for cryptographic applications, which is not what we're doing. You want it to be impossible to infer the hidden state. So like you might be using these random numbers to send like across the internet or something. And so you might, like some attacker might observe these values, xn, xn plus minus 1, like a whole sequence of them. And if they could infer the state behind there, then they could infer the next values of that sequence. And then they might be able to break like whatever encryption you're using or like whatever it is. So you definitely don't want that for cryptographic applications, but we don't care because we're doing simulations, so it doesn't matter. Okay. Right. Okay. So like this just making the point that like for convenience reasons and efficiency, actually, you generally want to like have produce integers as the range, like the range of things that come out in these x's are actually going to be integers. So rand itself produces like floats by default, but you can ask rand to produce other things. And behind the scenes, there's probably going to be a rand producing a uint64 or something else like that. And then that will be transformed using some bit twiddling, which we're going to see in just a minute, into like a float 64. And that's just because like the kind of sort of discrete algorithms that are used to generate random numbers tend to be like based on integers, and integer arithmetic is fast. So it's a good choice as sort of like the very base. Okay, and then of course you could like you normalize that into like 0, 1 just by dividing. Actually, you don't want to do that. In practice, there's this, actually you can't see all of this. Let me copy that out. Whoa, okay, that's not good. Okay, so I made the font too big. Okay, so like the rand, this is going to be my rand or something. So this I'm actually going to run this. I don't want to. Oh, no, it's fine, I suppose. So like this would be like roughly the implementation of rand. I'm not actually sure if this is exactly what's going on in Julia, but it's pretty similar. So what we actually do is we generate a random number. So this RNG is the state, actually. So we generate a uint 52, which is just enough bits to fill up the mantissa of a float 64. So all of the fractional parts. And then we set the exponent parts to say that this is a number between 1 and 2. This is just a trick. That's what this OR does. Some bit twiddling to like just set the bit pattern correctly. And then we subtract 1. That happens to be a really fast way from going to like a number between 0 and 1. And so yeah, it's an interesting little thing. Sorry, I'm just having a look at what's the next in. Oh yeah, okay. Yeah, so we don't really like, often we don't care about that hidden state, and that's why rand has like a version without the state in it. But Julia does manage that behind the scenes, and you can think of it kind of as a global, it's a global to every task that's running. So you can have like multiple threads or whatever running at once in Julia, or you could have things running concurrently. And so like each of those should have its own state at least. So that's good, we do have that. And that's why I was kind of saying before that ExoSure is really good, because you can have 1,000 tasks in Julia. You don't want them to all have the Messian twister behind the scenes taking up like several kilobytes and having to shuffle that, like initialize that state and shuffle it around. So yeah, we're able to like do much better by having a small state. Yeah, and you could also ask like, okay, where's the first value of rand? Like, where's the state come from? So like the initial state is often called the seed. Now I think there's a function called seed. If I've forgotten, no, I've forgotten. Yeah, there's a random.seed. So yeah, you can seed a random number generator with an initial. Oh, we need to go back up. Like with an initial state, or you can seed the global generator with an initial one, and then initial number, and then like the state behind the scenes will be seeded with that. And if you seed the random number generator, then every time you seed it with a certain value, you get the same sequence out again. So that's like really useful if you want to have some tests or something, which you do with your library, which depends on the random number generator. You probably don't want those to be different each time. You probably just want them to be the same. At least if they're sort of unit test style tests, you want them to be the same. Otherwise, you just like might have test failures just for statistical reasons, and that's really annoying when some things randomly fail. So you don't want that. Okay, yeah. Okay, so we're going to look at like now we're going to look at the kind of very simplest random number generator, or one of the very simplest ones. Not quite the very simplest, but yeah, pretty much the very simplest. I'm actually not quite sure what Andy was getting at with this little bit here about arbitrary numbers. You can like pick out a random number, not a random number, maybe an arbitrary number, by just like having an undefined array, and you just like pull some numbers out of memory, which whatever happened to be in there beforehand, like all these values, we can have one of them. We wouldn't know what distribution those are drawn from. They might be statistically dependent on each other. They very much probably are. There's probably going to be a lot of zeros in there as well, for instance. So they're definitely not uniform. Yeah, I'm not actually sure what the point was for that little bit, but yeah. It's a fun little thing. You can pull some random values out of memory. But yeah, let's make a pseudo-random number generator where we have a deterministic sequence. Okay, so a really simple one to implement is this one. And to be honest, when I first saw this, I was like really surprised that this would even work. Like, why would this simple recurrence? So you get xn, you multiply it by some number, you add some other number, and then you modulo m, that thing. And like, why would that very simple thing produce something even vaguely reasonable? I still kind of don't know the answer to that. This is actually, so there's like there's same problems with this one. You have to choose these A and C values really carefully, the M as well. You have to choose them really carefully, otherwise you get terrible things, which are not even vaguely kind of reasonable. They don't satisfy our properties. But if you do choose them quite carefully, there's some examples here, then like C is only one. Yeah, you can get some reasonable performance in terms of like the randomness. You really better choose an M, which is a power of 2. Otherwise, this whole thing is going to be incredibly slow on a computer. So as long as you do that, it's not too slow. Yeah, so we could actually implement this thing, and we will. I'd like to mention like just an example of this going wrong, which is RANDU. So this is like a famous random number generator with this recurrence here. This is a terrible choice of coefficients. So you can see in this case the C is 0. And it turned out that the numbers in this sequence were highly correlated with each other. So if you were to take 3 in a row and you make them into a 3D vector and then you plot them, then you plot all of those numbers that you get out of it, you get this diagram. So there's 15 planes here in this 3D space, and all the numbers lie on those planes. So the numbers are like highly correlated with each other. This RANDU was like IBM, like in one of IBM's machines for a while, and a lot of research was like performed on top of this random number generator, and it's probably a lot of it's just not correct because this random number generator was broken. So yeah, you really want to be choosing one that's good. And luckily, modern systems, people know how to choose reasonably good ones, and they've chosen reasonably good ones. So yeah, don't use RANDU. Okay, so let's make one. Okay, so what's this little bit of code? So it's just implementing what we saw. We've got some coefficients. There's this little function here. Oh, and in this case, what's the maximum length of the sequence? Can people tell me what the maximum length of sequence is for this one?
32.
Yeah, right, exactly. So it's 2 to the 32 because we've got this. Well, actually, we haven't specified these at UN 32s, but we probably should if we were doing this carefully. But yeah, like the modulus here is 2 to the 32. So the state effectively is 32 bits. So 2 to the 32 is like the maximum length of sequence we could have. And I think this one is chosen so that we do have that, which is interesting. So every single, even though the state is just 32 bits, we can choose these values A, C, and M such that we get every single value in 32 bits, which is pretty surprising to me as well, amongst the other things that are surprising about this. The fact that this even works. Yeah, it's fun anyway. So we can reproduce that plot there. So basically what we've done is we've just made a bunch of data with this. So we've started with a certain value of 808, and we just called the next function a whole bunch of times and put the data into this data array and then just plotted that. So what you can see here is this is the number, this is the iteration number, sorry, and then this is just the value of the random number generator at each iteration. And if you plot histogram, you can see that it's pretty much a uniform distribution. So between 0 and 1, we're getting a whole bunch of values out of this because we've normalized this here. And yeah, like every single bin, so the numbers near 0 are occurring just as much as the numbers near 1. So it has like reasonable properties. And it's not even that slow. But yeah, people don't use these ones, these linear congruential ones, much. Like I don't think for serious scientific work, I think people still use these because they're super simple to implement. So simple. So if you need something like quick and dirty, for some reason, like some low level reason, these are still a reasonable thing to use. Okay, yeah, and it says here that these are full cycles. So that means it can take every possible value in like of the state. Sorry about that. I think that's what it means. It does take every possible value for X. I'm not sure about the state itself. The state is X in this case. So yeah. Okay. Okay, so having seen that, so it's halfway. So yeah, let's looking at like using, how do you use RNG objects in Julia? So this is more of a library thing. So we just saw before the exo-shiro. It's just a very high possibility that I'm just pronouncing that wrong as well. Anyway, so this is a random number generator of a state object. So we can call rand with that one, and we get a number out each time. And this state changes as we do that behind the scenes. Yeah, and we can get things out which aren't floats. So if we want an integer out of that, we can get that. So if you want to get something of a certain type, you can just call the rand with the type as a variable here. If you want something out of a range, there's like a few different things you can do. Like if you want something between 1 and 10, you can call that. In general, if you want something out of an array, uniformly chosen out of the array, I think that's how it works. You can call this. So yeah, there's a few different like utilities that are all built into rand. Yeah, and if we were to create this random state, whoops, if we were to create that afresh each time, so 27, by the way, is the seed, then we would just get the same exact number out each time, because it's deterministic, right? Okay. Oh yeah, okay. So yeah, like here's a little example of using a common sequence of random numbers to generate a few different simulations. So imagine that we're simulating a random walk. So yeah, like a useful kind of thing you can do with states is to like reproduce the sequence, but use different parameters in your simulation. And so you're using the same random numbers, but using different other parameters. And that can like help you understand your problem a bit better because you're not just like lost in a sea of noise, basically. So this is a little bit of code here, which implements a random walk. We flip a coin to do one of 4 things. If it's 1, then we go left. If it's 2, we go up. So we have 4 different ways we can go, and we just step 1 unit in any of those directions. And there's a little bias, this alpha parameter, which we just add on each time. So it's pushing, this is like 2-dimensional coordinates, x and y. So we're sort of like pushing to the top right of the diagram each time. And we're just going to record the x's and y's that we get out of that, and we'll plot them. So I can do this. Okay, and there's a few different alphas we could choose. So this is the whole idea of like you might have different parameters in your simulation. So these alphas are the parameters that you've chosen. It's like there's more drift to the top right in the 3rd simulation than there is in the first, where you start out at 0. So let's just run all of that code there. Oh, okay. Oh, that didn't work. Oh, it will. It will. Here we go. Okay, good. Okay, so just to show those in a bit more detail for a moment. So yeah, so they're like a little bit of code at the bottom that I didn't go through. In one case, we've chosen the same seed. So we've got the same sequence, but we have different values for alpha. So we're kind of pushing this random walk in one direction, but depending on what alpha is, you kind of go more or less quickly in that direction. Whereas if you choose different seeds, you just really can't see because the randomness is more powerful than the drift in this case. So to see this drift that you've got, you would really have to run, you would have like the difference in parameters, you would have to run these simulations many, many times and do the averages over those simulations. So yeah, like it's kind of a useful technique to use the same sequence sometimes in the cases that it works. And you could generally look at it as a technique for variance reduction. So excuse me, you're trying to like make some estimates about this system based on like its parameters, and you'd like to have to do less simulations basically. So like the reduction of the variance of your estimates is kind of the idea that you get out of this. Okay. So we've seen an example of generating a uniform distribution between 0 and 1. That was our linear congruential one. The building one's exo-zero. So given that we have that, how would we build other distributions out of it? So that's the next bit we're going to have a look at. Okay, so yeah, sometimes it's really easy. Say you wanted a uniform distribution between A and B. So that would be a function to do that. You just multiply the value you get from rand by the distance between A and B, and then you add on like one of the ends. Excuse me. Yeah, that's enough to generate like a random uniform variable between two like inside an interval. Yeah, and here's another example where you might want to generate a random like a coin toss, basically a weighted coin toss. So P is P is the probability of getting sorry. I really should have brought a drink. Oh, I'm sorry. I'm gonna have to go and get a little drink. Oh. Yeah. So sorry. Oh, that's so funny. Okay, yeah, no, I just have a little cold and I didn't think to bring one. Oh, okay, thank you so much. Yeah. Thanks. Please wash it afterwards. I do have a cold. Yeah, my mistake. Okay. Right, where was I up to? Okay, so this is a coin toss. So we're going to generate a coin toss with some probability P for being probably for P for being, is it 1 or 0? 1. Oh, geez. So okay, yeah. So if we had more than one outcome, say 4 here, we could have like probabilities for each of those. They should add up to 1. So we could look at the cumulative distribution of those. That's what we're doing here. So let's look at that. So let's actually just plot that. Oh, I don't want to do that. I'm going to go bar. Okay, so this is an example where like we've got 4 possible outcomes. So 1, 2, 3, 4, and we'd like to sample each from like how outcome 1 should occur 0.1 at the time, etc. So that's our probability distribution. And the cumulative distribution function looks like this. So they should all add up to 1. They do. So this is essentially the probability of getting something which is 4 or less. This is the probability of getting something that's 3 or less, etc. And the cumulative distribution function is going to like, hey, it's going to play a really important role later because it's one of the ways of generating a good random number. Well, generating things from various distributions is a general technique using the cumulative distribution function. Okay, so and here's a technique. Here's a bad way of doing this, in fact. So given the CDF, you could generate a random number, one of the 4 outcomes using this algorithm. Basically, you generate the random number, and then you step through this array of CDFs. And when you get to one which is where the random number is above the CDF, then you just return that value. So that's what this while loop is doing. So we could actually try that out. And what we see is that it's the same as the intended CDF, probability distribution that we started with. So just showing those 2, they're the same. That's good. So we've generated 10 to the 6 samples here using this bad technique. Now, why is this bad? Well, it's not actually bad if the length of the CDF is only length 2, but if this is well, or I guess like this one here, basically reduces to this. But if you have a lot of possible outcomes, you have to step through this array, the whole array. Okay, so what we're going to see here is so yeah, this is an example of generating the binomial distribution. So if you've got this loaded dice which has probably P of landing on heads, and then you do a bunch of coin tosses n, and then you sum those values together, like 1 for heads and 0 for tails, whatever. Then that's the binomial distribution. So yeah, that's what this one will generate. I actually need to run this rand bit function from up here. Not sure if I ran that before. Okay, so So this is like, there's a known mean and standard deviation for the binomial distribution. That's what these are. Just showing, that's what it should be. And the statistics module has also has functions for computing those things. They're very simple. So if we were to use this binomial generation function and compute the mean and standard deviation from that, then we should see that those sampled versions, those estimated versions, come out really close to the ideal, the known values for them. In fact, they do. Yeah, so another thing that you should probably be aware of here is that the package distributions has all of the fun like distributions that you would normally like to use. There's a whole pile of them and they're all available. So for instance, the binomial distribution, you could use it like this. So the rand function in that case is overloaded with to like take a distribution. So we're going to sample from this distribution. And we're going to take that many samples. So if you do need to use some various different distributions which are of interest in statistics and simulations and other things, you could probably get them from the distributions package. It's quite a good package. There are some built into the random library though, of course. So we'll see those in a minute as well. So yeah, again, we could look. Oh, we've already done that. But we could look at the Oh, okay. Yeah. So the other thing this is showing is that if you have a distribution, this is like an ideal representation of this distribution. So the statistics function knows, sorry, the distributions function package knows the mean and standard deviation of these, the actual ideal values of those. So yeah, you can also query those just directly from the distribution itself without generating samples. Okay. Okay, so there's an example here for the exponential distribution. Think about time. What do we want to get through? Yeah, we should do this example because this is an important one. Okay, good. Okay, so yeah, there's like a whole pile of algorithms for generating random numbers from just different distributions, and there's a bunch of tricks, basically. There's this whole grab bag of tricks. So we're going to see a few of those tricks. Arguably the most important trick almost might be rejection sampling, which is surprising because it seems like a bad idea. We're going to see that a bit later. But also this is one of the other most important tricks here, which is the inverse CDF method. So yeah, so if we have an exponential distribution we'll probably just density this. We can plot some of those. Oh, no, let's do that again. Wow. I've talked all morning yesterday. I didn't have any issues. So sorry, I'm just having this really bad tickle. Okay, so yeah, if we plot this distribution, we've only got one parameter for this distribution. It's this lambda parameter. And it turns out that we only need really to implement one generator for the exponential distribution with lambda equals 1, because all the other ones are just scaled versions of that, which is really convenient. Okay, so where are we? Gone too far. Okay, so here's the magic thing. So it turns out that you can sample from this distribution here. So what you want is you want to take some x's such that they have this probability, which is given here. So it turns out that you can sample from this using this algorithm, which is absurdly simple. Oops, what's going on here? Oh, okay, whatever. Okay, the issue is that we're trying to overload randex, which already exists because random defines that. And Julia doesn't like that. So yeah, we can sort of sample from the one with lambda equals 1. We've got all these different numbers. And like you can see that they should all be clustered over here. So this is the red curve. Most of the probability density is like concentrated in this region here. So they really should be clustered around here. And you will get some out to infinity, but they're just really unlikely. Okay, so how do we derive this surprisingly simple little form here? So well, the first thing is you can, as I said, you can rescale these into each other. So that's what this lambda scaling is. We really just need to like figure out how to do it for lambda equals 1. Yeah, so the idea here is that you want to use the cumulative distribution function. So like actually just look at this diagram here to get an idea of what you're trying to do. Oh, actually, no, we need the CDF first. So the CDF is just this integral here. So the CDF at x is the probability that you've sampled something less than x, less than or equal to x. That's what this integral computes. Probably finding something less than or equal to x. So yeah, this has the properties that it always it doesn't decrease, so it's like always increasing or like flat basically. And it's 0 at negative infinity. Like if your domain is minus infinity to infinity anyway, then it's like 0 at negative infinity and it's 1 at infinity. Yeah, and it's just the inverse, and the inverse CDF is just the inverse of that CDF function. So this is the CDF. So we're going to plot the CDF. So if you just went and integrated that exponential, then you get that thing. Okay. So yeah, so this is the CDF here. Actually, we've got it here as well. Let's make it big though. So the idea of the inverse CDF method is you just like want to generate a random number in this range here. So this is the CDF, but for the inverse one, you generate a uniform random number between here and here, and you just look where it is on this curve, and then that's the random number that you return for the distribution. So you can invert the CDF. It looks like this. And there's just an extra little trick in this case to make this part here go away, the 1 minus p, because you're generating this p between 0 and 1. That means the 1 minus p is also a uniform distribution between 0 and 1. So you just don't need to do the 1 minus p. So you just put you can just put your uniform number right in here, and that's how you get it. You can end up with that. So the reason I said this is like important is that basically this works for anything where you can invert the CDF. So you can't always integrate like the probability density function and invert that nicely. So sometimes you just get a disgusting formula that's really complicated to compute, or you just can't do it. Like you can't do the integral. So sometimes you just can't do this. But in the cases where you can do it, it's just a really nice and simple way to get like any arbitrary, well, for the case it works, for getting any probability density function and turning it into a sampler for like numbers within that distribution. And you end up with some like analytical form. You can just put your uniform number in there and you get out the answer. Yeah, so it's nice and simple in the cases that where you can do those integrals and stuff. Okay, so let's see whether check where we want to get to here. So we need to get to this. We need to cover this. I think we're going okay. Yeah, okay. Well, we're going okay. Okay, so the Gaussian distribution, here's a really fun trick. This one's just a fun trick, so let's talk about it. So yeah, one way to generate values from the Gaussian distribution is to use something called the box-Miller transform. And basically this would be the function that you would use. So this isn't actually how Random and Julia is implemented. It's got a more efficient version and it's not using this method, but this is just a cool trick. So why don't we have a look at it? So yeah, so this relies on this trick. Actually, we can't see all of it. There we go. Instead of looking at the one-dimensional distribution, we could look at a two-dimensional distribution, which is Gaussian in both directions. So that's and that's something you can integrate easier. So if you wanted to find the integral of this thing here, wait a minute, what's going on? Oh yeah, okay, So momentary confusion. Yeah, so like say you just squared this integral here, you would get this thing. So like you've just got two copies of this, so we could make two dummy variables, x and y, and then put them both on the inside of this integral. So that's what we're doing here. And then we can transform it to polar coordinates and actually do the integral. So it's just like you can do this integral this way. It's a trick to be able to do this integral and to get the square of this integral. It's just like a way of actually getting the analytical solution to that. Because it turns out that you like in polar coordinates, you get this lovely little R factor, and that lets you do this change of variables with this new capital R, and just makes it possible to actually do the integral. So yeah, we can use that same exact trick to do sampling from the Gaussian distribution. Okay, so what have we got here? So this is just a contour plot of what this two-dimensional distribution might look like. So, but yeah, imagine Gaussian in both directions. Yeah, so the idea is that instead of drawing a random x and a random y, we're going to draw a random radius and a random angle. And we can get x and y back again from this thing here. So like this distribution here has got this big lump in the middle, right? In two dimensions. So yeah, we can easily draw a random angle. So this is like it's a radially symmetric. It's symmetric in the angle, so we just need a uniform distribution for the angle. And the radial distribution is simpler to draw from. So it turns out that we just need to draw an exponentially distributed thing, and we already had the way to do that from the previous example. So yeah, we can get the radius and the angle, and then we get two Gaussian distributed random numbers out of that using this x is r cos theta and y is r sine theta. So we get two different ones out from drawing the angle and the radius instead. So yeah, that's like a fancy little trick you can use. Oh, what's going on? I don't know what that's doing. Wow. No. Wait a minute. Okay, there we go. Sorry about that. Okay. So yeah, this little bit of code here just implements that, and it's just drawing a bunch of samples using that method, and we can see that and the red line is the ideal values that you would get out of it. You can see that it's really good. It's doing what it's meant to do. We've got a million samples here, so we should be getting a pretty good match with the histogram and the ideal PDF, and we do. So yeah, that one's good. That's just fun, I think. Rejection sampling is actually really important, and this is there's not a lot in here about this actually in the notes, but from a practical perspective, this is a surprisingly important method because it seems kind of dumb. So say you've got some like funny shape in the 2D plane, like in this case, we're just doing it as a circle because it's really simple. But like, say you had a really funny shape, and you have some algorithm to say, am I inside or outside that shape? Say you had that. So you could just generate uniform numbers in like a bounding box around that shape, just using a uniform distribution for X and uniform distribution for Y. So that's what we're doing here. So we've got a bunch of X's and Y's, which are between -1 and 1. And then we can just go, well, is that number, is that point inside or outside the shape that we're trying to uniformly find samples on? And if it's inside, then we like keep the sample. If it's outside, we just ignore it and try again. So that's rejection sampling. It's really simple. And can anybody tell me, like, what cases where would this actually be quite efficient in? Yes.
Itself, or in other words, I guess the bounding box approximates the actual shape fairly well.
Right, exactly. Yeah. So if the bounding box is if the shape almost fills the bounding box, then you almost always succeed the first time. So yeah, so say you succeeded 99% of the time, the second try, you also succeed 99% of the time. So that's actually a very efficient way. If you happen to, like, it doesn't even need to be like a square box. It could be some other shape, which is very easy to generate samples in. So maybe say it was a parallelogram or some other like easy to generate shape. Then yeah, it would actually be quite a good method. If you have this like a shape which is like highly complicated, but most of it's empty space, this is going to be pretty bad because nearly all the time you reject the samples. So yeah, we're definitely gonna take a break. Yeah, we'll take a break. One thing I want to mention before the break is that this is actually like an important component of what's called the ziggurat algorithm for generating random numbers in like a whole class of distributions, actually. And Julia's implementation of randn and a whole bunch of other fast like implementations actually use a variant of like a rejection sampling is inside the ziggurat algorithm. And it's way faster to do a first step of rejection sampling on this kind of shape that you match to the CDF in some sense. I think that's roughly how it works. And then if you fail, then you've got some like side things that you can do to make, to like fill in the spaces of the distribution where you couldn't make nice shapes on. So yeah, like rejection sampling is kind of like an important thing, it turns out, even though it seems kind of dumb, you can use it to create algorithms which are actually really, really fast. And yeah, so it's an interesting little thing. So yeah, if you want to look that up, it's the ziggurat algorithm. This one. Yeah, I don't know all the details of how this works, but yeah, it's extremely good. Okay, so we'll take a break. Sorry that was a little bit long, but we'll get into the second half later. Okay. Whew. Yeah, so we'll come back in, I don't know, 10 minutes. You'll mostly still be here anyway. Thanks so much for this. I was dying. I couldn't hardly speak. It was bad. Okay, I even brought these. So like I thought there was an off chance I'd have an issue, but I thought I was having an issue of like losing my voice, not being able to talk for other reasons. Oh no, it was social. I was just like I was at climbing and I was like talking to people there and yeah, and I talked to people for like an hour or more and it was fine. And then I kind of had a bit of a sore voice and I was like, I'll be all right. Hopefully. Yeah. Did you had something you needed help with? I'm going to turn this off for the moment. hoping it's working. Yes, okay. Yep, we're back on again. Okay, so let's get into the second half. I think I've been maybe going slightly faster than expected. No, that's fine though, because we've got an interesting example coming up. I'm actually kind of inclined to skip the Poisson one because this is really just another like trick to generate random numbers from another distribution, which is the Poisson distribution. And like I was saying, like these tricks aren't even necessarily used in like a production quality random number generator. You might use one of these much more complicated algorithms like the ziggurat algorithm, which relies on a bunch of pre-generated tabular data and a bunch of stuff, but it's just way faster. So yeah, like let's maybe just ignore this one because I don't think there's like anything super interesting about it. Yeah, and we can get onto discrete event simulation though, because I think that's what's relevant to your projects. Yeah, so although we did have an extra long first half, so that's okay. Okay, so discrete event simulation. What is it? Well, as I was saying before, it's about things that occur at discrete points in time. And there's sort of like, in some sense, nothing interesting that happens between those points in like those events. So you can advance your simulation. If you're doing a simulation, you can advance it to the next interesting thing, which is the next event that's going to happen. And there's no sort of continuous evolution of the system state that can happen in between. So you can use this for all sorts of things. Like there's certain physical systems even that you can use it for. We're going to, well, here's like a simple example. So we're looking at a call center. So I'm assuming that we have 5 workers at a donation call center, and they make telephone calls continuously. So whenever they leave a call, they immediately get the next person who's in the waiting list, and they talk to that person. And the duration of each call is like not known, but there's some distribution for that duration, and we're going to assume it's exponentially distributed. And the average time that someone spends on the call is 7 minutes. And so this little setup is going to be, we're going to try and like estimate how much revenue does this call center generate. So we're going to assume that if the call is less than 1.5 minutes, then it's no donation. And if the call is more than 1.5 minutes, then there's going to be a donation that person makes, which is proportional to the call time. So it's like a pretty simple model of what the donations might be. Maybe you'd have a distribution for that, actually. You probably would. But in this case, we're just going to say it's something simple. Yeah, and there's a factor in there for like how much they're going to donate. If they spend ages talking to them, then maybe they donate more. Like, it's kind of funny. Maybe they just needed a long time to be convinced. But anyway, this is a simple model. Okay, so we can simulate this with a discrete event simulation. So I guess like the kind of key things you should look for in this are like, what's the current state of the system? So you need to track that, and you also need to track the events that are coming up in the future, because those events will change the state. So that's what we're going to do. Yeah, so those simple assumptions lead to like a system which is a compound Poisson process. And so like a bunch of different systems that you might have with really simple assumptions, you could like, there's like a special name for them because they're like simple enough that someone studied them, and there's some analytical results. And this is one of those cases. So like the reason that's useful is there's the analytical results can be compared to your simulation, and you can like test whether like it's working or not in certain cases. For instance, like there might be parameters where you set a few things to 0, and then like in that particular case, there's some analytical results. And then you can check whether your code's working in those limiting cases. And we'll see some more examples further along where we can do that. Okay, so this code here is the simulation of those assumptions. So, okay, we're going to use distributions, random plots, and we're seeding the random number generator, the global one, with 0, so that we get the same thing each time, and the same simulation. Yeah, and this is our call duration. So it's this exponentially distributed thing with like mean of 7 minutes. Okay, so we'll put that in. And this isn't good. You can't even see it. There we go. So the amount of money as made is this function here, which we already discussed. 0 if it's less than 1.5, otherwise it's based on the duration. So we can put that in. Okay, so let's just have a look through this simulation function and see what's going on here. Okay, so the first thing is we need the state. Yeah, so these are like, well, okay. Just trying to think like what the actual state in this is kind of really trivial. This is a funny example in some ways because everybody is always like the workers are always on a call, and we're not tracking the length of any queues or anything like the waiting callers or anything. We don't care about them. So we're not really tracking any state here. We're mainly just tracking the events. And the most of the stuff that's going on in this function is just like recording some things so that we can plot our simulation at the end and see how it's going. So what we've got here, and we're going to need this to calculate the revenue, because we need to know how long each call lasted. We've got the, I guess we can think of that as part of the state. I'm not sure. I suppose that's state relevant to what we're trying to calculate. So we've got the length of each call that the workers are currently on. So there's 5 workers. And okay, so this is important here. We're going to keep track of the possible future events. So to start with, all the workers have just started at the beginning of the hour with whatever call duration that they started with. That's what these 5 different call durations that we've made are. And the time at which those calls are up is the current list of events. So that's because time is 0 and they all started exactly the same time. So that all their calls are up whenever the duration of that call is up. But later on, we need to add the current time to this duration. Okay, and then we're going to track the total revenue and the current time in the simulation. And then this is a log of the times at which the events happened and the revenue which happened during those events. And we're just going to keep track of all those so we can plot them. Okay, so the structure of this loop is basically that we're going to keep going until, well, this is while true, so we're actually going to break further down here because it's just convenient to break out of the loop somewhere else rather than at the top. So like the first thing you need to do when you're simulating one of these things is find the next event. So that's what's going on here. We find argmin as a function which calculates the index, which is the minimum of the minimum thing in the array. So we're looking for these just the times, right? So we're looking for the time, which is the next time in line for the call to end. So we found the index. So this index here is just like which worker was it? Which like call center worker is on the call when the call ends. Okay, so the time at which it ends is just that. And then at the end of this 60 minutes, we're going to just like log the last, the like end of the simulation, basically. So if that happens, we're just going to break out. But otherwise, we're going to record what time it was for this event, which is the call ending. And we're going to look at the money made for that call and add it to the revenue. And then we're also just keeping track of how that changed over time. And Okay, so as part of this event, the worker is immediately going to get on call with the next person in the waiting list, I guess. And the duration of that call is just, again, a call duration. But the time that that call ends is the current time, so that's important, plus that duration that we just generated. Yeah, so that's all it is to it. So yeah, that's the general structure of a discrete event simulation. When an event happens, you figure out the time of the next interesting thing, the next event to happen. You don't do that. You you remove the event from the list of things that's happening, and in this case, we're replacing it with a new event, which is the next the next time that work is going to finish. So yeah, it's the general structure. You find the next event to happen. You do the effects of that event. In other words, you change the state of the system to like take account for that. And then you add any new events which have generated from that back to the list of events. So that's generally how these things are structured. And then there's this utility function here. This is just for plotting. So it's not particularly interesting. It's just for making a pretty plot. So why don't we just grab all that code? Sorry, what's that? Oh, that's actually a good question. So, well, what do you think happens? So, like, what's going to happen is it finds, so this thing argmin, actually, let's see what happens. We will call argmin. So say we had, event. So say like the first and second one were both 1 and the other ones were larger. So they can be something else. Oh, what's going on here? Can't type. So it just happens that argmin just returns the first one in line. So that is actually fine. So what we're going to do in this case is then just replace the first index of the worker with a new event, a new duration. But then the next time we go through the loop, we're going to find the other person. So we keep going through the list of possible workers, which all occurred at the same time, and we will update the simulation that way. So as long as they don't depend on each other, as long as this sort of state transition doesn't depend on the order in which you do it, then it's fine. Yeah, it just like does the right thing. Yeah, just turns out that way. But yeah, if we were to find like all of the ones which had like the same, like finishing at the same time, then yeah, we might have an issue here. Or if like the state depended, like that, the state update depended on the order in which things done, that could be a problem. So it depends on the structure of the problem. In this case, it's fine. Now, I didn't paste that code in. Okay. Do I even need to? We've got a graph down here. I'm going to do it anyway. Okay, cool. Whoa. It did actually work, and I'm not sure what has gone here. Okay. Okay, so we've got a plot here then, which shows the revenue over time. And this little stitch steps function is just to make these like vertical and horizontal lines. So just to make it look prettier. So this simulation has just been run 3 times with different seeds essentially, because we didn't reseed it in between. So yeah, you could run this many times and take like an average of all of these graphs, and then you would see the average revenue generate over time. You could calculate the rate, like, because this is like a stationary time type situation, like the state updates don't really depend on the time itself. So really the like rate of revenue generation shouldn't really depend on time. So you could calculate that rate from this. You could do all sorts of like statistical properties, like calculate all sorts of properties from this. Okay. Yeah, so these type of models can be used in all sorts of places, and there are some like kind of carve outs. So when, like I said, like there's nothing continuous happening in time, Well, maybe there could be, but you might only have non-interesting things happening in continuous time. So like if you want to simulate an ideal gas with little particles bouncing around a box, you can actually do it with a discrete event simulation. And the reason you can do that is each particle has a velocity and position, which changes continuously, but you can calculate, oh, I forget actually the full details. I think it's something like you can calculate the next time that that particle would collide with something else, and you put that on the list, and that can be invalidated in the future if something else collides. So like the next possible time it could possibly collide with any other particle could be like entered into this list, and then you can step forward to like the next time something collides with anything. So then there's like that collision will generate some new velocities for those particles. And so you can like remove any collisions which were dependent on like the state of those two things like continuing in a straight line, right? So you can do it for certain cases where like sort of nothing interesting happens in continuous time. Yeah. And the reason that that's actually a good idea is that like a discrete event simulation is skipping all the times in between, the like all the non-interesting times, like all gone, and you just don't need to simulate them. So it could be efficient. Okay, so we've got another example here. Sort of from logistics again. So if we're thinking about a health clinic with a waiting room full of patients. So in this case, the state of the system, we've got the number of patients that are in the waiting room. We have the number of patients which are speaking with the secretary, which probably is 0 or 1, probably. We could assume. The number of patients which is with each doctor and what the doctors are doing, that might be important to us, like what they're actually doing as well, could be. And yeah, the activity of the secretary, whether they're with the patient or they're on the phone or they whatever. Yeah. So yeah, the types of events, so those are the like, that's the state of the system. And then the types of events that could happen is like someone walks in the door, says a new patient arriving. Like the patient goes to see into the doctor's room to see them. They leave the doctor's room. They go and speak to the secretary. There's phone calls that the secretary has to answer and those kinds of things. So yeah. Yeah, so anyway, like each of those possible events causes the state to change. And so yeah, we would just simulate our health clinic by going to the next time that an event happens. So we keep list of all of the current things, the current events that can happen. We go to the next time an event can happen. Yeah, and see how that changes our state. So I think that's just, these notes are just talking about what I just said, I think. Okay, and there's just, yeah, there's a note here that like, there's a whole bunch of commercial software to do these kinds of simulations. Probably some of it's very expensive. Or you could just write your own depending on what your needs are. Okay. So on to queuing, I think this is more relevant to the assignment, if I remember, the project 2, sorry. Okay. Right, so yeah, it's like, so queuing is like a whole area of research in its own right. And there's a whole field called queuing theory, which deals with, so you just like literally have a queue of people waiting for something. That's the general vibe of it. You have a bunch of things which, like a bunch of like items or whatever on a queue, and the next one's going to be processed from that queue, that kind of thing. A bunch of people waiting for something to happen, whatever. So yeah, it could be all sorts of things. It could be like some jobs on a computer system. Those jobs are each waiting for the CPU to be ready so that they can run, for instance. Or you could have like a whole cluster of CPUs and you're trying to schedule those jobs onto the CPUs. It's like a very practical example that I've had unfortunately large amount to do with in my professional life. Is like scheduling work onto a whole cluster of CPUs. It's like, yeah, important problem. There's a whole pile of software you can download to try and make that work well. Yeah, so there's a bunch from queuing theory. There's a bunch of different names for like a bunch of like kind of simple assumptions, I guess, that the properties of the queues might have. So one of the simplest models is this MD1 queue. So personally, I don't know a lot about queuing theory, so yeah, go and look it up. But we'll talk a little bit about it here. So what MD1 is about is the M is about like how do the customers or like jobs or whatever they are arrive into the system. And we assume it's a Poisson process. So that's sort of like the simplest possible thing you might have for the arrivals, which is basically like some like things like doesn't matter about the state of the queue, doesn't matter about when things arrived previously. It's memoryless. Things will just arrive with a sort of constant probability coming in. So the M actually stands for Markovian or memoryless, which are the words for the same stuff. Like Markov processes being ones that don't have memory, where the like transitions in the system between like the states of the system only depend on the current state of the system. They don't depend on the previous history of the states of the system. Yeah, so it's like D in this like little acronym is that the durations are determined fixed values, and the one is that there's a single server. So you don't have like a bunch of different people at Kmart. So this is like irrelevant now with like, oh no, it's still relevant. Yeah, like so you go to Kmart. It's not the case. They instead of having all of these different like self-service kiosks you can go to serve yourself, there's only one of them. So that's what the one's about. So you've got the single queue, and that's feeding into a single thing where you get served. Okay. So yeah, that's like simple enough that you can do a whole bunch of analytical stuff. And yeah, don't know much about that, but there are results and they're in the notes. So, and you can answer a whole bunch of questions which you might want to know. Like, is it stable? So like if you have this queue, does it grow indefinitely? Is it possible the queue could become like, is it expected that it will become longer and longer, or is it like it will stay bounded? Yeah, and it's like, does it have a steady state? So if you just start the system off somewhere, does it end up like in the end, there's like a steady state of the system where like not much is changing. So yeah, you can ask questions about like how long do people spend in the queue, and like what is the distribution of waiting times? So are the customers going to be angry? Like, for instance, you might want to answer that. Like, if people suddenly have to, like, if occasionally people have to wait for 30 minutes in the queue, they're going to be really angry. So you don't want that. So like that occasionally you want to quantify maybe. So you might want to answer those kind of questions. Like, what's the distribution of how long people have to wait for? How often are they going to be angry? Yeah, and you could also ask questions about transients. So if you start the system off as empty, how long does it take for it to reach a fairly steady state, like with a fixed number of people roughly in the queue, that kind of stuff. Or you could say like, if there's like, if there's a sudden influx of people, how long does it take for that to like settle down after the influx kind of finishes? Yeah, so yeah, so that like there's enough kind of analytical tools that you might not need to make a simulation full of those. But like practically in real life situations, there's usually something weird that breaks your analytical model, and then you need to write some code, which is great because code is great. Maybe. Okay, so project 2 is an example where there's not actually analytical formulas for all of the cases. There's some limiting cases, I think, in project 2 where there's some analytical results and you can check your code against them, but the general case is going to be simulated. Like will simulate stuff that you can't just work out analytically. And there's also just a mention of 2 other like acronyms here for other types of queues, or like other types of systems, I guess. So MM1, you've got the service times. Instead of being fixed, the D, I think that was the D, wasn't it? Yeah, the duration of like being served is like fixed in MD1, but MM1, it's also exponentially distributed instead of being fixed. MM1K, the service times are exponentially distributed, and there's a queue capacity of size K. So yeah, I guess there's only so many people who can fit in Kmart, so I guess it's a pretty big queue capacity though. The customers will be angry. Anyway, okay, so yeah, in those cases, you can also get some closed form formulas for like the steady states and stuff. And those would be in terms of this inter-arrival rate. This is like the inverse mean time between arrivals into the queue and the inverse service, sorry, the 1 over muse being the mean service time. Yeah, okay. Oh, you mean why did they use that parameterization, or? And just like not using mu instead, or? I'm not sure why the parameterization is chosen, to be honest, but yeah. I mean, you can talk in terms of rates, or you can talk in terms of times. So you could talk in terms of like it's completely reasonable to parameterize things in terms of like what was the duration of service, but you could also parameterize it in terms of how many services can you do per second or minute or whatever it is. It's like it doesn't matter. Those are equivalent. They're just inverses of each other. So you could choose whatever parameterization you feel most comfortable with, presumably, but I guess this might be the standard one. I don't really know. Okay. So yeah, like we can look through this this simulator. So again, this is like very specific to this particular queuing situation. And we're going to see next some code which can do more general like discrete event simulations where like the kind of core of the simulator itself is generalized and you just use that same core all the time, but you can customize it by putting your own data structures and stuff in. So that will be nice. Because this, as you can sort of see, this like structure is the same. You just like find the next event, you see how it changes the state, you add new events to the system. That stuff always, the general structure is always the same. So, okay, so this queue simulator here, this is the whole thing. So, okay, let's see if we can get it on one page. Okay, so here it is. There's some stuff off the end here. Let's make that bigger. There we go. Okay. Yes, this queue simulation function, we are going to put in the maximum time of the simulation, and we've got these 2 functions we're passing here. So these things are, this function is going to be called to get the time of the next arrival. Actually, it's not the next arrival, it's the, well, it's the time from now of the next arrival, and we'll add the current time to that in the simulation. This one here is a function which determines how long the servicing that thing will take. So how long is someone at the checkout for? So in in this MD1 thing, this service function is just going to be a function which returns a constant. And I think that's down here. We've got one in here somewhere. MD1. So yeah, in that case, we just return this constant value. So an anonymous function returning a constant value in that case. And by the way, you might think that this is like pretty kind of inefficient to just have this whole function which just returns a constant, but luckily Julia's functions have types for each possible unique function there is, and so Julia will know to like generate code with that function in mind. So that function will be inlined into this, and the cost will be like as if you'd put the constant in by hand. So that's nice. No cost for that. Cost-free abstractions. Okay, so how does this all work? So yeah, we're going to keep track of the current time. We are going to, this is honestly not the best name for a variable. I should change this maybe, it would be easier. So this is actually the length of the queue. If it's not the queue, we're not keeping track of the details of the queue. This is just the length of the queue. So the initial length of the queue is 0. By default, but you can put something else if you want to. And the capacity of the queue is infinity by default. But you could put something non-zero into that. Okay, so okay, and the other thing, we're going to keep track of this thing which is in this code called queue integral. And what that is the integral of the queue length. So the queue length is a function of time, right? So it goes up and down as events happen, as people get served, and as arrivals happen, the queue length goes up and down. So we can integrate that over time, and that could be used to calculate the average queue length. And that's actually what we're returning from this simulation, is just the average length of the queue, which is the queue integral over the total time of the simulation. And this function itself doesn't keep a track of logs, so we can't make a pretty picture, but we will make one of those in a bit of code further down. Okay. So yeah, again, similar sort of situation for the code. We just keep going until we hit the end time. And we're just going to keep some temporaries around these prev things, the previous value of time, the previous value of the queue length. And so we'll just keep those around just for the purposes of computing things like the queue integral. Okay, so what we need to do then is we need to find the next event. So in this case, we've really just got the next service or the next arrival is going to happen next. So there's two possible events that could be happening. There's a service or an arrival. That's the only things that could happen. So this bit here will deal with the event as if there's a service, if someone's gone to the, well, if someone's finished at the kiosk or the self-service, like checkout or whatever, then we'll be in here. And if they are, if someone arrives, then we'll be in here. Okay, so yeah, if they've finished being served, then the queue will get shorter, and yeah, so that then the time will be set to the next service time. And yeah, if the queues, if there's still people in the queue, then we're going to set the next service time to be this thing, and otherwise it's infinity because nobody's in the queue. Alternatively, if it's a new person arriving, then we've updated this time to the next arrival, which it's like we're keeping track of when the next arrival was going to happen. Previous in the simulation, we calculated when the next arrival was going to happen, and we're keeping track of that. So we update the time to when that arrival is, and yeah, it's just similar stuff. So we change the state of the system to like for this event. Yeah, and then the only thing we're really keeping track of in the simulation in terms of statistics is this queue integral, and that we just, that's just the like length of the queue during the time interval, which is q prev, and that's multiplied by the time interval So yeah, that's just doing this rectangular shaped integral over time, like a bunch of rectangles added together, basically. That's all that is. Okay. And then at the end, it just returns the average length of the queue, which is the total time, or the queue integral over the total time. Right. And it's not that much point running this, I guess, because it's just going to spit out some values which we can see on the bottom here anyway. There's no pretty pictures. But yeah, you can put in some values for the parameters. And by the way, if you haven't seen them yet, then you can get all these symbols just with backslash lambda like that. Does everybody know the most important thing about the symbols, which is how to get the smiley faces? Okay, no, so I have to show you that. So tada equals 100. Sine of tada. Anyway, the point being that Julia does have Unicode identifiers. So if you want to use another language, or if you want to use emojis for your identifiers, and nobody else will be able to read them, then go for it. Yeah. Anyway, but more seriously, like, I guess, but less fun. If you need like the mathematical symbols, then go and look up what LaTeX does with its naming of its symbols, because you can get all of them. So like, and if you want like identifiers like this kind of thing for mathematical indexing, you can have these things, which can be really useful in some cases. If you just want your like code to look like your mathematics in the paper that you're copying, whatever, then you can have that. And yeah, so I think that's probably the main serious reason for it. But yeah, there's lots of funny reasons. I think there's a package actually in the package ecosystem called watchjuliaburn.jl, which please go and look at it. if you just want to be amused. Anyway, it's remaps a bunch of stuff to use emojis and other things, awful things. Anyway, going back to the lecture. We're nearly done, I think. Yeah, so you can run this Q simulator for various different these different queuing theories, I guess. Theories like assumptions that we might have made about how our queuing works. And you can put in these anonymous functions for the arrival and the service functions. And you could also put in a capacity for the queue. Or you could put an initial queue length, which was also provided. It's over here somewhere, initial queue. Sorry? This thing here. Oh yeah, okay, so that's an anonymous function. So like, maybe I'll do this. So map is a function which, so if we wanted to call sine on each of these, we could do this, right? So we map the function sine over this array. If we wanted to do something more interesting, like if we wanted to do, well, it's not that interesting, but like, let's say we wanted to go sine of x plus plus x squared or something. So we could do this. Oh, what's going on here? Okay, so basically this thing makes a little function. It doesn't have a name. It just has functionality. It has a single argument x, and it has an implementation, which is that. So this is the same. It's just that if you have 0 arguments, then you use the brackets like that. That's all it is. Yeah, so that like the simulation is going to evaluate this expression exactly. So it needs to pass in some code that can be evaluated. It can't just give it a value. It needs to give it a function to evaluate. Because like each time somebody arrives, we need to calculate possible arrival time for them. So that's where we're going to just draw from this exponential distribution, right? Yeah, okay. Good question. Yeah, so we could do that kind of thing. Okay, so yeah, we just get numbers out of this, but so it says the load on the system is, what's a row actually? Oh, okay, so yeah, okay. It's just based on the parameters. Right, so this is like saying, oh, well, these, we've got some values from theory basically. So these are formulas that if you went and looked at how queuing theory itself and like understood about how like you deal with these things analytically, then you can like derive some formulas, some things like this for these different scenarios. And so you've got some like nice closed form solutions for those. And yeah, we could see whether those actually match up with our simulator, which, I mean, obviously the simulation is only doing estimates of these, it's not actually calculating like the like true, like the actual mean, it's an estimate of the mean. So, but yeah, they're close, that's good. Okay, what else do we want to say about this? Oh, another thing, like I guess to note about this is we're trying to calculate these parameters here by sort of doing a time average of the behavior of the system. And that's not something that always makes sense. Like say your system's parameters, or say your system is like non-stationary in some essential way, like it doesn't really have like a long-term fixed behavior. You really shouldn't just average things over a long time. But in this case, there's nothing like interesting in terms of like there's no non-stationary behavior of this. And so you can just do like a long time average and you can calculate some sort of ensemble properties. So you can like do a simulation in time and then you can make statements about what if you did that simulation itself many different times starting from 0 and you looked at then some particular time in like t equals 100 minutes into the simulation and you looked at the distributions of things at that time. Instead of doing those thousands of simulations of full length, you might just be able to do one single simulation and then look at how things vary over time. And if you have a system which has like enough stationarity, or that's probably not even a word, but it's like stationary in some sense, like, or ergodic is like the technical term, then you can like turn these ensemble averages, which are really expensive, into time averages, which are really cheap. Yeah, that's like a really useful thing to be able to do in the cases it applies. And it is extremely hard often to prove that you can do that, in fact. Question?
The stationary would be, for example, if the Q just grows. Is that one example or not necessarily?
Yeah, right, exactly. Yeah. So if the Q just grows without any bound, then like you shouldn't do time averages. It doesn't make sense. Like actually there is no value for the mean. It's infinity or something. Like as long as you run the simulation even longer and it will go up. So yeah, definitely that's the case. Yeah. I'm trying to think of a good examples like yeah, I don't know. There's lots of physical systems which people think are ergodic and they haven't been able to prove. I think even simple cases like you have a bunch of billiard balls inside of like an oval, if I remember. Like I think people prove that's ergodic and the behavior, like these time averages can replace ensemble averages. But like that was so hard to prove, it's absurd. Like you think it's like such a simple system. These balls are bouncing around, there's no friction, they just bounce off the edges. And then like whether you can say that's like ergodic or not is like, yeah, anyway, it's surprisingly nearly impossible in a lot of cases to actually prove this works. But often you just kind of believe it's good enough and you do it because it's so much more efficient. Okay, so this does talk a bit in the notes here about like, why would you want to run multiple trajectories? Like there are examples, like if you're looking at transients, you start with 100 people in the queue and you know that they like that kind of tails off, but you want to know after 50 minutes, has it tailed off yet? So you'd like often cases where you put a transient into the system and you want to know at a specific time after that, like what's the state of the system? What's the distribution of like how many people are in the queue or something? In that case, you might need to do, well, you would need to do multiple runs. So you do the simulation lots of times and then And then at each time after this transient like event, you can see the distributions that are there. Yeah. So in that case, yeah, you wouldn't want to do ensemble, like a time average in that case. And that is the end, I think, for today. Let's see if there's any. Oh, there's just a note here that, yeah, we're not tracking much about the state of the system here. We are just tracking how many people in the queue, but you might need to track something more about the state. For instance, if you wanted to know like the distribution time of the waiting time for the customers, then you might need to track individual customers. So yeah, then depending on what you want to know, you might need more information in the state. Okay, so that's like perfect timing to stop. And next time we will talk about a more structured approach. So we've made all these bunch of while loops, and they're each like specialized for our particular situation. But next time we'll talk about how do you make it so that you can have like the while loops in one place, and then you plug in like events and stuff, which is your domain knowledge somewhere else. And you don't need to keep rewriting the same while loop all the time. And the same like code to search for like the next event and those kind of things. Yeah, okay. So yeah, that's it for today. Thanks for coming.